Alright, continuing with, I think, lecture 8, and on polarization, dielectrics, Van de Graaff, and capacitors. Polarization doesn't belong in there. But anyway, let's see what happens.
Electric fields can induce dipoles in
Starting over.
insulators. Electrons in insulators are bound to the atoms and to the molecules, unlike conductors where they can freely move. And when I apply an external...
Alright, so theory about why how insulators get charged. So he's going to argue that it's just atoms getting lopsided and proton ends moving one way and electron ends moving the other way and just creating a lack of symmetry. I'm going to argue that there is no communication between the atoms of the substance, and whatever happens on the surfaces happens on the surfaces. Yeah, but we'll see. It's inconsequential to the interior.
field, for instance a field in this direction, then even though the molecules or the atoms...
Let me just say they don't transmit ions, so they don't transmit pressure. So one atom doesn't connect to another and say, I have more electron pressure, I'm going to share it with you. So pressure, like heat, doesn't move through them well at all. That's the definition of an insulator. It's not a complete insulator, it's just a really lousy conductor, in a sense.
may be completely spherical, they will become a little bit elongated in the sense that the electrons will spend a little bit more time there than they used to, and so this part becomes negatively charged and this part becomes positively charged.
Yeah, a few weeks ago I would have bought something like that, but now I'm pretty certain you don't need to polarize the atom, you just need to ionize it, and you created a charged atom. The atom itself is charged. That is, from all perspectives, it is a positive or a negative.
And that creates a dipole.
Doesn't need to be a dipole. Just doesn't.
I discussed that with you already during the first lecture, because there's something quite remarkable about this, that if you have an insulator, notice the pluses and the minuses indicate neutral atoms, and if now I apply an electric field, which comes down from the top, then you see a slight shift of the electrons. They spend a little bit more time.
So, again, he shifted them, so it's sort of an artificial disconnect. He took them from one side and just moved them to the other side, so they're obviously by themselves now. No. But this doesn't have to have anything to do with... It implies a conductor, in a sense, right? I mean, the idea that all of them would move, all the electrons would move or cascade through the material, that doesn't really imply an insulator. That implies a conductor. So I would argue that whatever charge gets on an insulator comes from the outside.
Up and down, and what you see now is, you see
it's an imposed charge.
A layer of negative charge being created at the top and a layer of positive charge being created at the bottom. That's the result of induction. We call that also sometimes polarization. You're polarizing, in a way, the electric charge. The substances that do this, we call them dielectrics, and today we will talk quite a bit about dielectrics.
So dielectrics aren't insulators? I don't know. I mean, I think they're both. So I think dielectric can be both insulator. I don't think a dielectric can be a conductor, so I think we're sort of stuck with their insulators, generally speaking. I think there's a semantics problem, because I don't think there's any difference between the two things.
The first part of my lecture is on the web. If you go to 802 web, you will see there a document which describes in great detail what I'm going to tell you right now. Suppose we have a plane capacitor, two planes which I charge with certain potential, and I have on here, say, a charge plus sigma, and here I have a charge minus sigma. I'm going to call this free. You will see very shortly why I call this free, and this is minus free. So there's a potential difference between the plate. Charge flows on there. It has an area A, and sigma free is the charge density, how much charge per unit area. So we're going to get an electric field, which runs in this direction, and I call that E free. And the distance between the plates, say, is d.
So their physics is sort of obsessing about the field. The field is just the consequence of this imbalance between the radiation that's coming down. So it's more negative or more positive in terms of the mix of these little force bits. But the point is depending on what they hit, it's really going to decide whether there's attraction or repulsion. If they hit something that can't detect the difference, doesn't have any ions, doesn't have any positive or negative elements to reflect in a completely negative way, then it's not going to be significant. Wrong word. I'll come up with a better one.
So this is a given. I now remove the power supply that I use to give it a certain potential difference. I completely take it away. But that means this charge here is trapped, cannot change. But now I move in a dielectric. I move in one of those substances. And what you're going to see here now, at the top, you're going to see a negative induced layer, and at the bottom, you're going to see a positive induced layer.
So it's just like bringing the plates essentially closer together. You have a positive plate at the top, a negative plate at the bottom. He's just going to put another set of plates, essentially just duplicating the same process, so it's sort of redundant. And the real end result is changing the distance between the two plates by putting in the dielectric. So it's going to do essentially the same thing as moving the plates together.
I call it plus sigma induced, and I call this minus sigma induced. And the only reason why I call the other free is to distinguish them from the induced charge.
So at least it's a decent word, induced, which is sort of implying that the force, the energy, the radiation, is what's going to cause the charging. And that takes time. See, I would argue that the first effect, so when you put your another material in on a charged surface, the first effect is it's either going to push protons down and electrons up, or it's going to push electrons down and protons up. And that difference is the first phase of being charged. And the second phase is that now that the electrons are up, let's say, or down, their pressure, because the pressure is pushing them, they're going to start ionizing. So the first electron knocks it down. I mean, the first force bit knocks it down. Then the next bits of force are going to push electrons into it by doing exactly the opposite to the negative ions. Well, we'll see how it works.
This induced charge, which I have in green, will produce an electric field which is in the opposite direction, and I call that E induced. And clearly E free is of course the surface charge density divided by epsilon 0, and E induced is the induced surface charge density divided by epsilon 0. And so
I would suppose that there's no point in talking about it as it's moving through something. So you could argue that there's gravity until it starts hitting your matter, and then it gets kind of messy about exactly what the gravity's doing, because then it becomes more like chemical transmission of the pressure. Just like inside the Earth, there's more pressure inside the Earth because the gravity, all the matter above it is imposing that pressure through acceleration. So to say that the force is inside of these things in the sense that it's still in the same form would be like saying gravity's in the same form as it moves through me, and it's really not in the same form, especially the parts of it I'm absorbing. The parts that are moving my matter are certainly not going the speed of light anymore. So there's a huge this field is not the same field going through empty space as it is when it's going through a substance.
The net E field is the factorial sum of the two. So E net, I give it the vector, is E free plus...
Right, so all you have is left is the little space you have between the two. So the space you have between the insulator on the two surfaces is all you have left of your space. If you minus these E fields, that would be this. That's all you have left when you subtract the two. Seems pretty obvious.
E induced.
And when you say that's your distance, then that's like moving the plates that close together, which is opposite of doing work, because the plates want to move together if the insulator wasn't there. And so you're basically going to have to subtract some of the energy out of the two plates. So the insulator's basically going to absorb energy.
Factorially added. Since I'm interested, I know the direction already, since I'm interested in magnitudes, therefore the strength of the net E field is going to be the strength of the E field created by the so-called free charge minus the strength of the E field created by the induced charge. Minus because this E vector is down and this one is...
It's just kind of obvious, right? I'm just saying he's just getting around to it, but the point is you can obviously see one is down, one is up. One is 90% of the other one's value, so the only thing left over is going to be that 10%. So you've lost 10% of your field strength.
In the up direction.
You've lost 90% of your field strength.
And so if I now make the assumption that a certain fraction of the free charge is induced, so I make the assumption that sigma induced is some fraction B times sigma free. I just write now an I for induced and an F for free. B is smaller than 1. If B were 0.1, it means that sigma induced would be 10% of sigma free. That's the meaning of B. So clearly, if this is the case, then...
So he's basically just said what I said. Right, you only got 10% left.
Also, E of I must also be B times E of F. You can tell immediately they're connected. And so now I can write down, for E net, I can also write down E free times 1 minus B. And that 1 minus B now...
sometimes I just get lost. Why you have a perfectly good equation, the E minus the E thing, you get it done. Why are we doing more of this stuff for? You already figured it out.
Call 1 over kappa. I call it 1 over kappa. Our book calls it 1 over K. But I'm so used to kappa that I decided to still hold on to kappa. And that K, or that kappa, whichever you want to call it, is called the dielectric constant.
So it just has to do with how capable. It's not the same as. It's not an insulating quality. It's a state change. Well, let him say it.
Dimensionless number.
I know.
So I can write.
Dimensionless number is not very helpful. So it's a constant that's dimensionless number. It's obviously going to have a number. Every material is going to have a number, so I don't know why he says it's dimensionless. Beyond the fact that I guess he's saying it will be assigned based on the substance. So every substance will have a different number.
Write down now, in general, that E, and I drop the word net now. From now on, whenever I write E, throughout this lecture, it's always the net electric field. It takes both into account. So you can write down now that E equals the free electric field divided by kappa, because 1 minus B is 1 over kappa. And so you see in this experiment that I did in my head, first bringing charge on the plate, so...
well, kappa divided into the... Somewhere in here has to be the distance between the width of the insulator.
Potential difference, removing the power supply, shoving in the dielectric, that the E field will go down by a factor kappa. Kappa for glass is about 5. That would be a major reduction. I will show you that later.
All right, E free is the original charge. Kappa, I just don't know how the kappa could possibly be the same. I mean, a millimeter glass or 2 millimeters of glass or 3 millimeters, it seems that's going to make a difference. So they must be considering there to be very little distance between the two surfaces, and there must be an assumption in this equation. The insulator is filling the entire void between the plates, essentially. That's got to be the assumption, because it's got to matter how thick this stuff is. So they're basically just saying as thick as it can be.
If the electric field goes down in this particular experiment, it is clear that the potential difference between the plates will also go down, because the potential difference between the plates V is always the electric field between the plates times D. And so if this one goes down by a factor of kappa, if I just shove in the dielectric not changing D, then of course the potential between the plates is also going down. None of this is so intuitive, but I will demonstrate that later. The question now arises, does Gauss' law still hold? And the answer is yes, of course.
See, these equations are all, the E field is just a representation of the geometry of where the things are positioned. So I would argue that you're probably better off with math that just recognized what the force is coming from, not the force. I mean, it's the light. If you were going to do light, you wouldn't worry about the photons in the air. You'd worry about how many you created at a surface.
Gauss' law will still hold. Gauss' law tells me that the closed surface integral of E dot dA is 1 over epsilon times the sum of all the charges inside my box. All the charges, the net charges, that must take into account both the induced charge as well as the free charge. And so let me write down here net to remind you that. But Q net is of course Q free.
This argument is just basically pointing out that the insulator isn't providing any charge, so it's not changing the internal circumstance, and it's not adding anything, so it can't possibly change the amount of charge inside the Gauss surface, because it doesn't have any.
Plus Q induced. And I want to remind you that this is minus, and this was plus. The free charge, positive there, is plus, and at that same plate, if you have your Gaussian surface at the top, you have the negative charge, Q induced. And so therefore, Gauss' law simply means that you have to take both into account. And so therefore, you can write down 1 over epsilon 0 times the sum of Q free.
So the argument's basically that whatever the other Q has, it took it from the other Q.
But now you have to make sure that you take the induced charge into account, and therefore you divide the whole thing by kappa. Then you have automatically taken the induced charge into account. So you can amend Gauss' law very easily by this factor of kappa. The dielectric constant is dimensionless, as I mentioned already. It is 1 in vacuum by definition. 1 atmosphere gases typically have dielectric constants just a hair larger than 1. We will most of the time assume that it is 1. Plastic has a dielectric constant of 3, and glass, which is an extremely good insulator, has a dielectric constant of 5.
5 isn't all that big a number. So the dielectric constant doesn't have anything to do with the ability, doesn't have to do with, just trying to think of the difference between the, like, it's not going to prevent sparks. So it doesn't have anything to do with sparking. So it doesn't have anything to do with breakdown voltage. It has to do with charge density, how much charge you can put on the substance. Maybe that's it. Yeah, so you want a high number to make more reactionary charge. So the higher the number, the better if you're trying to increase the density of the charge. And they're obviously going to kill the voltage.
If you have an external field that can induce dipoles in molecules, there are substances, however, which themselves are already dipoles, even in the absence of an electric field. If you apply now an external field, these dipoles will start to align along the electric field. We did an experiment once with some grass seeds, perhaps you remember that. And as they align in the direction of the electric field, they will strengthen the induced electric field. On the other hand, because of the temperature...
Okay, so they'll strengthen it, which means they somehow must be, yes, they're aligning, unlike magnetism, where you would have the opposite effect. The grass seeds are sympathetic to the field. So again, I don't know exactly how you did the grass seed. I don't know what fluid it was in, so there's a lot of things I'm suspect of whether there's a parallel between the two at all.
Of the substance, these dipoles, these molecules which are now dipoles by themselves, through chaotic motion will try to disalign. Temperature is trying to disalign them. So it is going to be a competition on the one hand between the electric field which tries to align them and the temperature which tries to disalign them. But if the electric field is strong, you can get a substantial amount of alignment.
Come on.
Permanent dipoles, as a rule, are way stronger than any dipole that you can induce by ordinary means in a laboratory. And so the substances which are natural dipoles, they have a much higher value for kappa, a much higher dielectric constant than the substances that I just discussed, which themselves do not have dipoles. Water is an example, extremely good example. The electrons spend a little bit more time near the oxygen than near the hydrogen, and water has a dielectric constant of 80. That's enormous. And if you go down to lower temperature, if you take ice of minus 40 degrees, it is even higher. Then the dielectric constant is 100.
Right, so it doesn't mean it's a good conductor, it means it's a good reactor through a field. Because it already has a bunch of things in it, a bunch of ions, I would argue. And so they just align with the field.
I'm now going to massage you through 4 demonstrations, 4 experiments. One of them you have already seen. And try to follow them as closely as you can, because if you miss one small step, then you miss perhaps a lot. I have 2 parallel plates which are on that table, as you have seen last time. And I have here a current meter. I put it an A in there, that means amp meter. And
so this really is an important part of physics, is that you have a whole bunch of these little experiments. And the idea is to come up with a model that matches them all. Where I would argue things like, you know, the fact that the single slit, they're using a different Huygens theory than for the double slit. And then you actually have the slit experiment that's done with a mirror, which makes absolutely no sense because apparently, you know, that's an artificial image that's projecting the pattern. You know, it's like a non-location, a non-second slit. The second slit's being invented inside of a mirror, so how would the wave function survive inside of a mirror? That should collapse the function. So, you know, there's lots of, but it's like this idea, you really do have to stack up all the phenomenon as it's revealed in these experiments and then create a model that honestly deals with all of them consistently. And I say they sort of fail at doing that.
And the plates have a certain separation d. I'm going to charge this capacitor up by connecting these ends to a power supply. And I'm going to connect them to 1500 volts. I'm already going to set my lights because that's where you're going to see it very shortly. I'm going to start off with a distance d, so this is going to be my experiment 1, with a distance d of 1 millimeter. And the voltage, V always means the voltage, the potential difference between the plates is going to be 1500 volts. Forgive me for the 2 V's, I can't help that. This means here the potential difference, and this is the unit in volts. Once I have charged them, I disconnect. It is very important. I disconnect the power supply, for which I write PS. That's it. So the charge is now trapped. As I charge it, as you saw last time, you will see that the ammeter shows a short surge of current. Because as I put charge on the plates, the charge has to go from the power supply to the plates, and you will see a short surge of current, which will make the hand of the ammeter, as you will see on...
See, this is the part, like, you know, he's done this like 7 times now, so this is a, you know, I'm just being critical. This is just an obvious part that if you really thought about it, you don't need to explain something as simple as this, that the current going on, obviously there's a current for to charge the plates, we got that. 7 explanations of that fact is just unnecessary. Yes, the capacitor has to be charged. It has to absorb current.
On the wall there, go to the right side, just briefly, and then come back. This indicates that you're charging the plates. And now I'm going to open up the gap. So this is my initial condition. There's no dielectric. And now I'm going to go D to 7 millimeters.
So the point would be, if it was a battery, the capacitor is just matching the voltage on the batteries. He's using a power supply, it just matches the voltage on the power supply. You can't pump more on it because you're already, once you charge it, it's charged. It won't accept any more voltage because it doesn't, you need to pump higher voltage in to get more voltage in. You have to have a voltage difference for voltage to move.
And this is what I did last time. The reason why I do it again, because I need this for my next demonstration. If I make the distance 7 millimeters, then the charge, which I call now Q3, that is really the charge on the plates, is not going to change. It is trapped. So there can be no change when I open up the gap. That means the ammeter will do nothing. You will not see any charge flow.
Well, you can't see any charge flow because you have it disconnected from the power supply. Jesus. It can't go anywhere. You don't have the ammeter tied to ground or something. You don't have it connected to anything. Therefore, yes, no charge goes through a wire that's not connected to anything.
The electric field E is unchanged. Because E is sigma divided by epsilon 0. If Q3 is not changing, sigma cannot change. So, no change in the electric field.
So again, that's why I'd say this all goes kind of south, because clearly as you move the plates apart, you're really going to change the reactions between the players. And as I pointed out, when they're close together, their attraction is going to be strong. They're moving into 3-dimensional space, the ions. So that's what depressurizes them, is the fact that they have more room to exist in. And there's no source of more or less, for that matter. So if you make more space, there has to be a consequence. The consequence is the pressure goes down because they're not banging into each other as much or as hard. And as you increase the distance, then the attraction reduces, which means they all kind of push back down into the matter. Now they're on a single plane, and now they're pushing against each other really hard. So, the interesting experiment would be to see how far you can crank them apart. Before the inverse square law thingy and all that crap destroys the voltage altogether.
But the potential V is now going to go up by a factor of 7. Because V equals E times D.
I suppose technically they will just stay charged, positive and negative. They won't have any interaction with each other at a certain distance, very little, but they'll just be charged, with a lot of charge.
E remains constant, D goes up, V has to go up. And this is what I want to show you first, even though you have already seen this. And I need the new conditions for my demonstration that comes.
I suppose at some point you'd end up with a breakdown voltage. Technically you could keep moving them apart, the voltage keeps going up, but there's got to be a point where it just stops going up at any kind of quick rate. It goes up just a tiny bit with more and more distance. So this probably is a proportional curve of some kind. I mean, you get a lot of voltage difference in the beginning and then it dies off
afterwards. I'm going from 1500 volts to about 10,000 volts. It goes up by a factor of 7. You're going to see that there. There you see your ammeter.
So I think you could have just skipped that. That 4 minutes was just a, that was just redundant.
I'm going to, you see the, this is this propeller voltmeter that we discussed last time, and here you see the plates. They're 1 millimeter apart now, very close. And I'm going to charge the plates. I will count down so you keep your eye on the ammeter. 3, 2, 1, 0, and you saw a current surge. So I charge the capacitor. It is charged now. The voltmeter doesn't show very much, 1500 volts. Maybe it went up a little, but not very much. But now I'm going to increase the gap to 7 millimeters. And look that the ammeter is not doing anything. The charge is trapped, so there is no charge going to the plates. But look what the voltmeter is doing. It's increasing the voltage.
He just keeps saying that about this amp meter. I just don't know how it could be. It's not connected to anything. You disconnected it from the power. How could it read anything? It's not connected to anything.
It's now approaching almost 10,000 volts, although this is not very quantitative. And now I have a gap of about 7 millimeters, and that's what I wanted. You've seen that the plates on the left side here are now farther apart than they were before. So that is my demonstration number 1, a repeat of what we did last time. So now comes number 2. So now my initial conditions are that V is now 10 kilovolts. So that's the potential difference between the plates that I have now. And D is now 7 millimeters, and I'm not going to change that. At this moment, kappa is 1. But now I'm going to insert the dielectric. So I take a piece of glass and I'll just put it into that gap.
Right, so he says he's not going to change the distance, but clearly by putting the glass in, he's changing the distance essentially. He's same difference. He's changing the surface, the differences, and that's all that really matters is the distance from surfaces. I mean, so much of this physics is this surface thing. It's a hugely important thing. All the diffraction happens surfaces, internal reflections in glass, all surfaces. Surfaces are huge. And, when it comes to ping pong balls bouncing between charges, surfaces, distances are a hugely important thing.
Q3 cannot go anywhere because I have disconnected the power supply. So Q3, no change. If there is no change in the free charge, the amp meter will do nothing. So as I plunge in this dielectric, you will not see any reading on the amp meter. But as we discussed at length now, the electric field, which is the net electric field, will go down by that factor kappa. That's what the whole discussion was all about. That's going to be a factor of 5. And since the potential equals electric field times D, but I keep D at 7 millimeters, I'm not going to change it. If E goes down by a factor kappa, then clearly the potential will also go down by a factor kappa. So now you're going to see the second part, and that is as it is now, I'm going to plunge in this glass, 7 millimeters thick, I put it in there. You expect to see no change on the amp meter, but you expect the voltage difference over the plates to go down by a factor of 5. So you will see that the propeller voltmeter will have a smaller deflection. You ready for this? There we go. Now you have a smaller potential difference, but there was no current flowing through the plates or from the plates. When I take it out again...
Well, again, the current can't flow because we're not connected to a power supply. So that's moot. So we don't know whether... well, I guess he's going to do more experiments, so I should just shut up about that. All right, so what I would argue, okay, is that the voltage drop is, again, just like putting the plates closer together. He's doing almost, it is sort of negative work in a sense that dropping the glass in gravity is negative work. But anyway, yeah, continuing. I would argue the charge is being placed on the glass, and the glass is actually being charged at the surface of the glass. So let's see what happens. See, when he pulls it out, I don't think you're going to go back to 10,000 volts. You're going to be a little short.
The potential difference comes back to the 10,000 volts.
Yeah, see, I didn't... I guess I could go back in the video here. See if we can find that. See, it's not a very good reading, but we got right about here is the mark. Well, I could do the needle itself. Alright, so that's the mark. And see what we get before he plunges the glass in. Alright, I'm going to play it from there.
The net electric field will go down by that factor kappa. That's what the whole discussion was all about. That's going to be a factor of 5.
Alright, come on.
And since the potential equals it down by a factor of 5, so you will see that the propeller voltmeter will have a smaller deflection. You ready for this? There we go.
Alright, that's where it started, and that's where it
now
comes
you have
back.
A smaller potential difference, but there was no current flowing through the plates or from the plates. When I take it out again, the potential difference comes back to the 10,000 volts.
Yeah, it did go back.
So that's demonstration number 2.
I did that for myself. Sorry.
Now we go to number 3. But before we go to number 3, I want to ask myself the question, what actually happens with the capacitance when I bring the dielectric between those plates? Well, the capacitance...
Well, the capacitance has to go up because the voltage went down, so something always has to make up for the difference. So, and I'd argue the glass is now charged, probably.
Is defined as the free charge divided by the potential difference over the plates. That's the definition of capacitance. And since in this experiment, as you have seen, the voltage went down by a factor of kappa, the capacitance goes up by a factor of kappa because Q3 was not changing. And so, since the capacitance, as we derived this last time for plain plate capacitors, I still remember it was the area times epsilon 0 divided by the separation d, since we now know that with the glass in place, that the capacitance is higher by a factor of kappa, this is now the amendment we have to make to calculate capacitance. We simply have to multiply now.
Right, so glass is 5, so but again, there's got to be an assumption here about distances, because it's got to matter whether you put a very thin piece of glass in or a very thick piece of glass. It's got to make a difference. Got to.
By the dielectric constant of the thin layer that separates the two conductors. This is the layer that has thickness d that is in between the two plates. In our case, I brought in glass.
So yes, so it's always filling the whole void. And that should just be, that's an assumption in this equation. This equation doesn't mean anything unless you're assuming the entire void is filled by the insulating material.
I could write down a few equations now that you can always hold on to in your life, and you can also use them in the two demonstrations that follow. And one is that E, which is always the net E, when I write E it's always the net one, equal sigma free divided by epsilon 0 times kappa. There comes that kappa that we discussed today. Let's call that equation number 1. The second one is that the potential difference over the plates is always the electric field between the plates times d, because the integral of E dot dl over a certain pass is the potential difference. That's not going to change. And then the third one that may come in handy.
I don't know, this potential difference and voltage, I just don't know why they just don't say pressure, because that's all it is. It's pressure. Pressure over a distance is proportional.
Is the one that I have already there. C equals Q3 divided by the potential difference, which in terms of the plate area is A times epsilon 0 divided by D times kappa. Let's call this equation number 3.
Which is just saying, well, I've got to fix this.
Now comes my third.
That, again, if the pressure of the bits is increasing, that means you can't have as many in the same location because they're pushing very aggressively. So your density has to go down. And if your voltage goes down, then you can have more of them. So I don't know how to... if you thought of light, like little LEDs repelling each other based on the light they're producing, you could sort of get it that if they're producing a lot of light, they're going to repel each other. You can't fit too many LEDs. But if they're producing a little bit of light, then they can get a lot closer together because they're not pushing as hard.
Experiment. In the third demonstration, I am not going to disconnect my power supply. So now, in number 3, I start out with 1500 volts, just like we did with number 1. But the power supply will stay in there throughout, never take it off. We start with D equals 1 millimeter, just like we did in experiment 1.
This would be an interesting experiment with a battery, just because, theoretically. Because if you increase the voltage to 10,000 volts and then you shove that back into the battery, for the voltage drop, that would be sort of interesting. But you can't get to the 10,000 volts with the power supply connected, so that's the trick. So yeah, there won't be any, it'll be a gradual pushing of the power back into the power supply.
No glass. I'm going to charge it up, just like I did with number 1. And of course I will see that the ammeter will show this charge. See a surge of current. Now I'm going to increase D to 7 millimeters. Now something very different will happen. from what we saw in the first experiment. The reason is that the potential difference is going to be fixed because the power supply is not disconnected. The power supply stays in place.
Right, and the voltage difference just always moves from high to low. So the pressure, as you're cranking it apart, you're creating higher voltage, but it won't stay there because there's a lower voltage to go to now. And the lower voltage is the power supply. So even though the power supply is 1500 volts, the plates are going to create whatever, 1501, and that 1 volt is going to keep going back.
Look now at equation number 2. If that V cannot change, and if I increase D by a factor of 7, now the electric field must come down by a factor of 7. And so now the electric field will come down by that factor of 7 because I go from 1 millimeter to 7 millimeters. Now the electric field changes because D goes up. In case you were interested in the capacitance will also go down by a factor of 7 because if you look at this equation, kappa is 1. If I make D go up by a factor of 7, C goes down by a factor of 7. Just look at this. Simple as that. So C must also go down by a factor of 7.
All right, so even though the voltage didn't drop, so at least that's not a reason for the capacitance to drop. So it's just the kappa number that's dropping it now. So there's something about the insulator that destroys capacitance, and that probably has to do with the fact that maybe it's absorbing the charge. So it's stealing some of the density of the charge itself. Maybe.
Nothing to do with dielectric. Nothing. And so Q3 must now also go down by a factor of 7, because if the potential difference doesn't change, if C goes down by a factor of 7, Q3 must go down by a factor of 7. This goes down by a factor of 7, this doesn't change. So the free charge goes down by a factor of 7. And what does that mean? That means charge will flow from the plates, away from the plates. And so my ammeter will tell me that charge is flowing from the plates, and so that hand there will go to the left. And so as I open up, depending upon how fast I can do that, charge will flow from the plates in the other direction. The charge will flow off the plates, and that current meter will show you every time that I open it a little bit, it will go to this direction. So let's do that first. No dielectric involved. Simply keeping the...
Right, so that's where you're losing it. So as you're moving the plates apart with no insulator, with nothing in between, tied to the power supply, as you're moving them apart, the voltage is escaping essentially, and with it some of the density. So you're losing both density and voltage. You're losing number and pressure.
The power supply connected. So I have to go back first to 1 millimeter, which is what I'm doing now. I have here this thin sheet to make sure that I don't short them out. It's about 1 millimeter. And I am going to now connect the 1500 volts and keep it on. And as I charge it, you will see the current meter surge to the right, right? That always means he charged the plates. So there we go. Did you see it? I didn't see it because I had to concentrate. Did it go like this? Good. So now it's charged. We don't take this connection off. It's connected with the power supply all the time. And now I'm going to open up. And as I'm going to open up, the potential remains the same. So this voltmeter doesn't dividend. It will stay exactly where it is because 1500 volts remains 1500 volts. But now, as we open up, we're going to take charge off the plates. And so I expect the ammeter to go to the left. Every time that I give it a little jerk, I do it now, it went to the left. I go it now again, I go to 2 millimeter, go to 3 millimeter, go to 4 millimeter, make it 5 millimeter, 5 millimeters, 6 millimeter, and I finally end up at 7 millimeters. And every time that I made it larger, you saw the hand go to the left. Every time I took some charge off.
Yes. And the charge went off because as you move the plates apart, the positive and negatives become less and less real as necessary things. They don't have to be there anymore. There's no urgency because there's no strong attraction. So they're just going back home to the battery, no, the power supply.
So that is demonstration number 3. Why did I go to 7 millimeters? You guessed it. Now I want to plunge in the dielectric. So my experiment number 4, I start with 1500 volts. I start with D equals 7 millimeters. And I'm not going to change that. There is no dielectric in place, but now I put the dielectric in. So kappa goes in. What now is going to happen? Well, for sure, V is unchanged because it's connected with the power supply. So that cannot change. What happens with Q3? Look at this equation. When I put in the dielectric, I know that the capacitance goes up by a factor of kappa. C will go up by a factor of kappa. If C goes up with a factor of kappa, and if V is not changing, then Q3 must go up by a factor of kappa. Follows immediately from equation 3. So this must...
So we've just done the opposite again. We're just making, so we've pulled the plates apart, but we don't have the advantage of the higher voltage. But we're basically just pushing them back together again by putting the insulator in. So we're now making this separation between surfaces very small, which is making a lot more of excitement for all the charges that are left. And they're repressurizing. Wrong word. They're going back from where they left. They're coming back again because now there's a reason to be there because the two surfaces are close. That's it.
Go up by a factor of kappa. What does that mean? That charge will flow to the plates. I increase the charge on the plates, and so my ammeter will tell me that. And so my ammeter will say, aha, I have to put charge on the plates, and so my ammeter will now do this. And that's what I want to show you. The remarkable thing now is that the electric field E, the net electric field E, will not change.
Says you.
And you may say, but you put in a dielectric. Yeah, I put in a dielectric, but I kept the potential difference constant, and I kept the D constant. And since V is always E times D...
But again, the distance isn't constant, technically. You've reduced the distance to tiny distance. So, again, whatever. I've made my point.
If I keep this at 1500 volts, and I keep the 7 millimeters, then the net electric field cannot change. It's exactly what it was before. That is the reason why Q3 has to change. Think about that. Because you do introduce induced charges on the dielectric. And you have to compensate for that to keep the E field constant. And the only way that nature can compensate for that is to increase the charge on the plates, the free charge. And so that's what I want to show you now, which is the last part. So I'm going now to put in the dielectric. And what you will see then is that current will flow onto the plates. So the propeller will do nothing. It will sit there, and you will see this one go clunk when I bring in the glass. And then it goes back, of course. It's only a little charge that comes off, and then it will go back. So as I plunge it in, you will see charge flowing onto the plates. There we go. You ready for it? 3, 2, 1, 0. And you saw charge flowing onto the plates. When I
It probably, like I said, I don't know if that glass still had charge on it, but I mean, that's sort of, could be a factor. But I'm just saying this is probably correct, but I just mean the glass isn't getting uncharged.
Move the glass, of course, then the charge goes off the plates again. You see that now. I've shown you 4 demonstrations. None of this is intuitive. Not for you, and not for me. Whenever I do these things, I have to very carefully sit down and think what actually is changing and what is not changing. I have no gut feeling for that. There is not something in me that says, oh yes, of course that's going to happen. Not at all. And I don't expect that from you either.
Yeah, well, this is the problem with their not really having a mechanical theory for exactly how this pressure is manifest. What makes the voltage and what makes the elements that contain the voltage. Well, the atoms, they're atoms, for friggin' sake. You know, and every atom is going to have a different dielectric in the sense that a kappa, because every atom has a different capacity to convey pressure. That's, the conductors do it well, the insulators do it poorly. Alright, so I think that's enough for this video, and so if you're still there, thank you for paying attention and whatnot, and giving a damn and being interested. So, till the next time, and such. I don't think I need to draw anything. Just like to do this for the hell of it now that I have the capacity to do it. I like that little fade. I wish I'm gonna have to switch the camera. This camera is way too slow, so I have to change that, which is always dangerous, but I guess I'll try changing it and such. So till the next time, thank you very much.